All right, adrenaline. It's what gives us that speed, that need. But adrenaline is actually R4, 1 hydroxy. There's the 1 hydroxy. 2 methylamino, ethyl, benzene, which is the ring, and it's a 1,2-diol. Now, do not worry, we're not going to be doing molecular structures like this, but this is where molecules come in, and molecules are so much more diverse than ionic compounds. Ionic compounds can only combine in certain ways, but with molecular compounds, they can combine in many, many ways.
Besides unlocking our body's resilience, the mind can also unleash superhuman speed. We instinctively call on that power when the brain spots a hazard too deadly to confront. Rather than face it, we push our bodies to the limit to escape. A wildfire blasts through the Southern California hills at terrifying speed. Caught in its path, a policeman accelerates faster than a racehorse. That life-saving burst of power is from inside.
Strong winds have sent flames racing up tinder dry hillsides today. 4,000 acres have now burned in Ventura County.
Officer Dan Perkins is trying to reach residents trapped by the approaching forest fire.
It was pretty hectic. There was a lot of fire and smoke. Visibility was pretty low.
On the approach road now. I'm going to try to get through to them.
Trees were falling partway in the roadway on fire. Fences were on fire. The house that they were at wasn't on fire yet, but it was going to be soon.
As he gets closer, Dan's body goes on alert. The fire could erupt at any moment.
Folks, get in your cars and follow me out. Quickly, quickly!
They started to go to their cars, and that's when the firestorm came over. It was, 60, 70 feet above me when it blew over. I thought that was it. I thought I was going to die.
An exploding fireball can outpace an Olympic sprinter and normally would engulf Officer Perkins. But his heightened state of alert triggers a powerful biochemical reaction. Adrenaline sends his body into overdrive, cutting loose strength he didn't know he had.
Adrenaline is a very neat hormone. You focus. It heightens all senses from your hearing, your smell, your thought processes so that you can be very focused to get out of a dangerous situation.
As Dan senses danger, the disaster center in his brain jumpstarts his body, and he runs for his life. That instant response triggers a series of critical reactions. Just above Dan's kidneys, glands inject the hormone adrenaline into his bloodstream. The adrenaline boosts his heart rate. Blood now races to his muscles quickly. Adrenaline signals his liver to flood the body with glucose, blood sugar for fuel. But even that won't save him. What really kickstarts Dan's sprint for safety is instant energy. It's there in our muscles, stored for just such emergencies.
The human body has a great resource in that it stores energy in preparation for emergency situations. And it's kind of like a high-energy battery. It just stores this energy, and so when you need to, you have this quick burst, and you utilize that energy. It's called ATP.
ATP, adenosine triphosphate, is the energy molecule that keeps us alive. ATP fuels our muscles. It can be made by burning glucose or fat. We store an emergency reserve of ATP in our muscles, available for instant action, turbocharging us on demand. For a few seconds, the energy burst turns Dan into a skilled sprinter. The 100-meter sprint, the ultimate test of human speed. The event lasts less than 10 seconds, time enough for a well-trained runner to call on a surge of high-energy ATP. For 4 precious seconds, his body accelerates at the maximum, consuming its emergency ATP supply. Now, peak performance is done. For the last 40 meters, the runner is actually slowing down. Then, with the race over, the body can stop. Dan's ATP battery needs to get him out of danger and to his car, 60 meters away.
I didn't even think about what I was going to do, where I was going to go. I just turned and ran. I don't think I've run faster in my life.
For a few key seconds, Dan has pushed his body to its limits. Just long enough to keep him alive.
Once I backed out, that's when I realized what just happened. I just shocked, and then I realized I had to go back in.
With the firestorm past, Dan returns to rescue the 8 survivors who had huddled in a swimming pool. By saving his own life, Dan Perkins was able to rescue 8 others. He was later decorated for valor.
Ionic bonds form when the combining atoms lose or accept electrons. That's what we covered in Chapter 7. Another way that atoms can combine is by sharing electrons. That's this chapter, Chapter 8. Atoms held together by sharing electrons are joined by a covalent bond, which forms a neutral group of atoms called a molecule. Oxygen gas consists of oxygen molecules. You see them to the right. That's O2. Each molecule consists of 2 covalently bonded oxygen atoms. O2 is an example of a diatomic molecule, a molecule that consists of 2 atoms, di meaning 2 atomic atoms. Other diatomic elements are H2, N2, Cl2, Br2, I2, and F2, and these are marked on your periodic table. If you look at the squares, you see in the upper right-hand corner, right underneath their mass, is the diatomic elements. They are in a box on the right-hand side with the symbol and a subscript of 2 to show that those are the diatomics. And once again, they're hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. A compound composed of molecules is called a molecular compound. Water is an example of a molecular compound, H2O, and you see its structural diagram to the right. A molecular formula is the chemical formula of a molecular compound. A molecular formula shows how many atoms of each element a substance contains. The molecular formula for water is H2O, meaning 2 hydrogens and 1 oxygen. Butane is commonly used in lighters and household torches. The molecular formula for butane is C4H10. Now, there are several ways that we can... Now, I'm going to use ammonia as my example. And there are 5 different ways that we can show ammonia and its formula. The first one is called a molecular formula. NH3 is its molecular formula. It shows the type and numbers of atoms only. The second, NH3, shows the bonding and non-bonding electrons. That's called a structural formula, and it gives some insight to its shape. A perspective drawing shows the bonds and a 3D shape. Now, the way it shows this is the closed bond or closed arrow is coming toward you, and an open arrow, which is dashed, is a bond going away from you. A regular line shows the bond in the plane of the paper. Ball and stick shows the 3D shape, but the bonds are exaggerated. The atoms are not that far apart, but notice it doesn't show any dashes or dots. It's just a ball and stick diagram. A space-filling diagram shows the 3D shape more accurately, but you can't see the bonds due to the overlapping electron clouds. Now, what we're going to do here is compare ionic compounds to covalent compounds. The electrons in an ionic compound are transferred. The electrons in a covalent compound are shared. The particles, an ionic compound is called a formula unit, and a covalent compound is called a molecule. The elements in an ionic compound are metals and nonmetals, and the elements that are in a covalent compound are metalloids and nonmetals. Conductivity when molten, which is melted or in solution, for ionic compounds, it's very high. Covalent compounds, they have low to no conductivity. The state at room temperature, ionic compounds are all solids, where covalent compounds can be a solid, a liquid, or a gas. For example, a solid covalent compound would be sugar. A liquid covalent compound would be water. A gaseous covalent compound would be carbon dioxide. The type of bonds in an ionic compound are all ionic, or in a covalent compound, they're covalent, but they're polar or nonpolar. Solubility in water. Most ionic compounds have high solubility in water, means they very easily dissolve, where for most covalent compounds, they have low solubility in water. They do not dissolve. The melting point for ionic compounds is high, where that of covalent compounds is low. And I have two examples. I have NaCl as an ionic compound and H2O as a covalent compound, salt and water. Now, below I show the equation of the formation of sodium chloride, where the sodium donates an electron to the chlorine, so the sodium becomes plus and the chlorine becomes minus, but notice that the sodium has no more valence electrons, so there are no dots on the right side, where chlorine goes from 7 to 8, so there are 8 dots in the chloride ion. And I also have the dots for water formation, and I have 2 hydrogen atoms, each which have 1 dot, and oxygen which has 6. And then what happens is they share, those unpaired electrons will share between them, and that will give oxygen 8 and hydrogen 2, which makes it stable. Now, in ionic bonding, elements fulfill the octet rule by either gaining or losing electrons. In covalent bonding, they're going to fulfill the octet rule by sharing electrons, and there are several ways they can be shared. The first is called a single covalent bond. The hydrogen atoms in a hydrogen molecule, as seen at the bottom of the slide, are held together mainly by the attraction of the shared electrons to the positive nuclei. 2 atoms held together by sharing 1 pair of electrons is called a single covalent bond. The electron dot structure is shown as H with 2 dots between them, or 2 H's with a dash between them. And the dots or the dash are called the shared pair of electrons. So you have 2 hydrogen atoms on the left. As they get closer to each other, they will share each, giving 1 to make a pair, and that forms a single covalent bond to make the hydrogen molecule. Now, the halogens, which is group 17 or group 7A, they also form single covalent bonds in their diatomic molecules. Fluorine, F2, which you see at the bottom, is one example. By sharing electrons and forming a single covalent bond, 2 fluorine atoms each achieve the electron configuration of neon. So we show it here using the arrows in the diagram. So each has 1 p electron that's unpaired, so those will pair. Or you could just use the dot structures, where on the left side each fluorine has 7, and as they get close, the 2 will be shared. Those unpaired electrons will then be paired. Now, there are three other pairs on the molecule that are not shared. They go by three names. They could be the unshared pairs, they could be the lone pairs, or the non-bonding pairs of electrons. So those 6 dots that you see around the outside of the molecule are the unshared electrons.
A covalent bond results when two atoms share electrons. In the case of two hydrogen atoms, each shares its single electron with the other. This sharing allows each to fill its electron shell with 2 electrons. The pair of shared electrons constitutes a covalent single bond. Let's now consider oxygen, an atom with 8 electrons. 2 electrons fill the innermost shell, and the other 6 electrons reside in the next shell. This outer shell needs 2 more electrons to complete it, the octet rule. 2 oxygen atoms form a covalent double bond by sharing 2 electron pairs from their outer shells. Carbon is perhaps the most versatile element on Earth, in large part because it contains only 4 electrons in a shell that can hold 8. To fill its outer shell, carbon forms 4 covalent bonds with up to 4 other atoms. In a molecule of methane, carbon shares electrons with hydrogen atoms, forming 4 covalent single bonds. Although this molecule is relatively simple, carbon often forms the backbone of large, complex molecules. With each carbon atom able to bond to 4 other atoms, carbon-based molecules are incredibly diverse. Triple bonds are rare, but nitrogen gas molecules, the most abundant molecule in the air we breathe, form triple bonds. The 2 nitrogen atoms share 3 pairs of electrons, allowing each to have 8 electrons in its outermost electron shell.
As you can see in the electron dot structure below, the oxygen atom in water has 2 unshared pairs of valence electrons. That means it has 2 unpaired electrons left over since it has 6 valence electrons. Those unpaired electrons can then pair with the unpaired electrons on 2 hydrogen atoms to form 2 single covalent bonds. So if you look on the right-hand side, you either see the dots or the dashes showing that there are 2 single covalent bonds between the oxygen and each of the hydrogens. Methane contains 4 single covalent bonds. The carbon atom has 4 valence electrons and needs 4 more to attain the noble gas configuration. So when it comes in contact with 4 hydrogen atoms, those 4 singles will all pair up to make 4 single covalent bonds. Double and triple covalent bonds. Atoms form double or triple covalent bonds if they can attain a noble gas configuration by sharing 2 or 3 pairs of electrons. A double covalent bond is a bond that involves 2 shared pairs of electrons. Carbon dioxide has 2 double bonds. If you look at the equation, the carbon has 4 singles. The oxygen each has 2 pairs and 2 singles. So what's going to happen is all those singles are going to pair up. So on the right-hand side, you see that the 2 singles from carbon on the left pair up with the 2 singles from oxygen on the left, and same thing on the right. The 2 singles from carbon on the right will pair up with the 2 singles on the right. So then when you're done, you will have carbon with 4 bonds, 2 to the left, 2 to the right, 2 double bonds, and each oxygen will have a double bond and 2 pairs. Similarly, a bond formed by sharing 3 pairs of electrons is called a triple bond. Nitrogen N2 has a triple bond. If you look at the 2 atoms on the left, they both have a pair and 3 singles. Well, those 3 singles will all pair up between them. And when you take 3 singles and pair them, you get 3 pairs or a triple bond. The octet rule cannot be satisfied in molecules whose total number of valence electrons is an odd number. For example, NO2. NO2 has 17 valence electrons, and you're wondering, how did you get 17? Well, nitrogen's in group 5, so that's 5. Oxygen's in group 6, but there's 2 of them. 6 times 2 is 12. 12 plus 5 is 17. So there's no possible way for everybody to have 8. So instead, what happens is there's more than one structure. And these different structures are called resonances. So on the left, we see nitrogen in the middle with 2 bonds to the right, 1 bond to the left. Well, that's 6 electrons plus the non-bonding pair makes 8. The oxygen on the right has 2 pairs. That's 2 non-bonding pairs, that's 4, plus 2 bonds, that's 4 more, that's 8. But let's look at the oxygen on the left-hand side. It's got a single bond, that's 2. It's got 2 non-bonding pairs, that's 4 more, that's 6. Plus it's got that 1 electron hanging out there by itself. That's the 7. So you're going to have 2 that are good and 1 that's not good. Well, the one on the right, same thing. The oxygen has 2 pairs and 2 bonds. That's 8. The nitrogen has 3 bonds and 1 pair. That's 8. But the oxygen on the right has a bond, 2 non-bonding pairs, and a single, which is a 7. So even though nitrogen dioxide cannot form an octet rule to make it stable, it is still a stable molecule. But it's just because the total number of valence electrons makes it impossible. Some molecules with even number of valence electrons, such as the compounds with boron, also fail to obey the octet rule. If you look at BCl3, the boron in the middle has 3 bonds. Well, that's 6 electrons. Each of the chlorine has a single bond and 3 pairs. That's 8. So the electrons on chlorine are satisfied, but boron is not. We call that an incomplete octet, because it is a molecule that's stable, but it does not have 8 electrons on the central atom. So that's an incomplete octet. A few atoms, like phosphorus and sulfur, can expand to 10 or 12 electrons, which is above the octet rule of 8. Sulfur hexafluoride, if you look at the sulfur in the middle, it's got 6 bonds. Well, those 6 bonds, 6 times 2 is 12. So sulfur would have what we call an expanded octet. Same thing with PCl5. The Cls all have 8 because they have a single bond and 3 pairs, but phosphorus has 5 bonds. 5 times 2 is 10. So that's also an expanded octet rule.
All right, so here's what's happening. There's a gas inside this tank. It's called sulfur hexafluoride. It's a super heavy gas. Sulfur hexafluoride. It's boring. It's inert. It's odorless. Okay, so it's normally boring. But here, watch this. I'm going to slowly pull the lid off. Okay. So that should be perfect. Gary, would you take that little end off over there as well? You see that? Yeah.
Yes.
All right, so let's see if. Oh, it feels pretty good. So let's see if we can float the boat. Okay. Ready? So here we go. Let's see if we can float the boat. Stay there, little guy. Tell me that's not awesome. Isn't that amazing?
That
is
is awesome.
Close to magic as you can. So is that, no, it's okay. Push it around. It's okay.
Crazy.
So this heavy gas is about 6 times heavier than the air that we breathe. And so I just have it coming through a tube here. And so I'm going to give us just a little bit more so you can kind of see what's going on. Here's what they use it for. Electrical engineers will flood a room or part of a semiconductor or something with this material because it doesn't allow electricity to, it doesn't conduct electricity. So here's a taser. Okay. All right, so look, so here's the taser. So when I put the taser down inside here, watch this. When I put it down inside, it stops.
Oh, it stops working.
And now when I bring it back out again, so they will keep it. So if you don't want something for arcing from one place to another. But the coolest thing is this: because it's inert, you can breathe it, and you might see something different. Ready? So
Can I go first?
So just stick your head way down inside and breathe in. Breathe in. Ready? Now talk to the nice people. Try it. Come here. Get in there.
Awesome.
All right. So, Amelia, Becky, get in here. Kyle, get in here.
That is awesome.
So ready? So breathe it in. Take a big hit. Don't waste it. All right, there you go. Now talk.
So sexy when you talk like that.
Crazy.
Oh my goodness.
Give us a sexy little walk, right? Give me. There you go. Ready? Come on, Kyle. Ready?
Like this. Breathe in like this. Ready?
Yeah, breathe out so you don't die. Okay, breathe in.
See, now we're okay?
Now we're okay.
Now we're good.
Yeah.
One more time, come on.
Barry White, I love it. It's a little Barry White voice.
Okay, we're gonna be right back.
I love this.
Wow, this is pretty amazing.
Okay.
I will tell you though, I am getting a little lightheaded.
Breathe out.
I'm happy to end
Is that crazy? That's what your voice sounds like when it's going through a heavy gas.
Okay.
Yeah, there it is. Heavy gas.
We all had heavy gas.
Yes. Thank you. You're very, very nice. And now you've got
Today, now we know that.
no, I mean the burning sensation will go away in about a week, so
Yeah.
it's fine. And your voice returns after 3 weeks.
Science guy, that was awesome, man.
Thank you. All right.
Covalent halides typically undergo hydrolysis. In many cases, the reaction can be vigorous and exothermic. When damp blue litmus paper is placed in this sample tube containing some phosphorus pentachloride, it quickly turns red. Solid phosphorus pentachloride reacts with moisture, forming phosphoric 5-acid and hydrogen chloride fumes. The hydrogen chloride dissolves in the water on the litmus paper, forming hydrochloric acid. Pure hydrogen chloride vapor is colorless. The misty appearance of the hydrogen chloride is due to water condensing in the region of the hydrogen chloride vapor. In this second test, a few drops of water are added to some solid phosphorus pentachloride, and then concentrated ammonia solution is placed in the watch glass just to the right of the sample tube. The smoke formed is solid ammonium chloride. Ammonia gas is often used as a test for hydrogen chloride vapor.
Okay, drawing Lewis structures for covalent compounds. A simple table that you can use to help you do these structures are the group number will tell you how many bonds they're going to have and how many non-bonding pairs. So group 1, which is only hydrogen, will always form one bond and have no non-bonding pairs, because by forming the bond, each bond is 2 electrons, and 2 is the electron configuration of helium, which makes it stable. If it is a group 4 element, carbon, silicon, those types, they will always have 4 bonds and 0 non-bonding pairs. And then as you go from 5, 6, and 7, they get 1 less bond and 1 more pair. So a group 5, like nitrogen, is always going to form 3 bonds and have 1 non-bonding pair. Group 6, like oxygen, will have 2 bonds and 2 non-bonding pairs, where group 7, like the halogens, chlorine, will always have 1 bond and 3 non-bonding pairs. Now, some things to remember. The element in the compound that forms the most bonds is going to be the central atom. So it's either going to be group 4, 5, or 6. 7 and 1 cannot be a central atom. Second, molecules want to be symmetric. So what that means is the elements are going to arrange themselves so they're as far apart as possible. And using the table above, and this is also on the back of your periodic table, you're going to fulfill the number of bonds and non-bonding pairs for each element in the molecule. A good thing to do is to bond all the elements together by single bonds and then add the multiple bonds until the rules above are followed. So let's start with NBr3. We have the rules. The element in the compound that forms the most bonds is going to be the central atom. Well, nitrogen's in group 5 and bromine's in group 7. So since group 5 forms 3 bonds, group 5 ends up in the middle. So what we do is we said that they want to be as symmetric as possible. So we're going to draw them so the BRs are off to the sides and the N's in the middle. And if you want to look at this and say, okay, I have fulfilled my 3 bonds. So nitrogen has 3 bonds. Group 7, bromine, only wants a single bond. So right now we're done with all our bonds because group 5 has 3 and group 7 has 1. Now, since nitrogen has 3 bonds, that means it gets 1 non-bonding pair. So if you look on the right-hand side, I have now added a pair of dots. So what does that mean? Well, those pair of dots are the non-bonding electrons in nitrogen. Bromine, which is group 7, is always going to have 3 non-bonding pairs, because if you draw just the dot structure of the atom, bromine has 3 pairs and a single, where nitrogen has a pair and 3 singles. So that kind of tells you what you want to look for. So when I'm done, every atom has now fulfilled the octet rule, because bromine, let's count. Start at the bottom underneath the R and go clockwise. 1, 2, 3, 4, 5, 6, and the bond is 2, so that's 8. We can do nitrogen. We can do the 2 singles, the pair, 1, 2, and then 2, 2, and 2. Each bond is 2. That's what's special about covalent bonds, is you get to add them in both of the atoms that they're in the bond. And then since the first bromine has 8, and nitrogen now has 8 with 3 bonds and a non-bonding pair, and then each of the bromines on the right and bottom also have 8. So we're going to do lots of these. The first thing is, you may want to get that table and make it available. So either you're going to switch back in your notes, or you're going to look at it. And when we do this, what I've done is I have taken the element that's the central atom, and I've underlined it just to make it a little bit easier to start with. When writing dot structures for molecular compounds, the element that makes the most bonds will be the central atom. Also, molecules want to be as symmetric as possible. So what we want to do is spread them out. So we're going to start with SiO2. If I were going to do SiO2, silicon is group 4, so it goes in the middle. And both oxygens are group 6, so they go on the outside. So if I'm drawing this, I'm going to draw an Si with an O on the left and an O on the right. Now, the rule is each oxygen gets 2 bonds. So I'm going to draw a pair on the left and a pair on the right. So that which doing the oxygen gets 2 bonds because it's in group 6. By putting 2 bonds on each side of the silicon, I have now fulfilled the fact that silicon needs 4 bonds because it's a group 4 element. But we're not quite done yet, because in order for the structure to be complete, you have to have 8 electrons on every atom, unless of course it's hydrogen, then it gets 2. So I look at this and my oxygen has 2 bonds, so that's 4 electrons. So I need 2 non-bonding pairs to complete my octet. So on the left and right hand side, I'm going to put my 2 non-bonding pairs. Now you might look at these and say they look a little bit different than we were drawing or saw before. The reason I'm doing this is to make it symmetric. I'm trying to put the electrons on the outside where they would be because they're repelling each other. C2. All right, C2H2. The carbon goes in the middle, but there are 2 of them. So the carbons go in the middle because the H's must be on the outside because they're group 1. So I draw it like this. 2 C's, 2 H's on the outsides. Each H gets 1 bond to the carbon, and the 2 carbons bond 3 times. So I put 1 bond to the carbons and 1, 2, 3 to the carbons together. So each H gets a single bond. Each carbon needs 4 bonds. That's why I need a triple bond, because the H can only form 1. So what must be left is the 4 on the carbon being all single bonds. Now, the rule is carbon has to have 4 bonds and no non-bonding pairs. Hydrogen has 1 bond, no non-bonding pairs. So that's done. I don't even have to draw any dots. So now we're going to do one that's similar but a little different. H2O2. So this time, the O's must go in the center because hydrogen must be on the outside since they only ever form a single bond. So it's going to look like this. My H on the outside, my O's on the inside. Now, the H's get 1 bond and the O's must bond to each other to make 2 bonds per oxygen. So I'm going to start with my bonds to my O's and my bonds to my H's. So there's one bond on the left of the O, one bond on the right of the O for both of them. So my bonds are now taken care of because oxygen's group 6, so it gets 2 bonds. Hydrogen's group 1, so it gets 1 bond. But we're not done. This is not like the C2H2. Carbon had 8 electrons because of the triple bond. Now, oxygen can't form a triple bond. It can only form 2 total bonds. So what's left is each oxygen is going to get 2 non-bonding pairs to complete their octet, because right now the 2 bonds make 4. So on the left, I put 2 non-bonding pairs, and on the right, I put 2 non-bonding pairs. Now to fulfill my octet, I count. My hydrogen has a bond, that's 2, perfect. My oxygen on the left has 2 bonds, that's 4. 2 non-bonding pairs, that's 4 more, that's 8. Same thing happens on the right. Now, what happens if we have 3 different atoms? HCN. The carbon is group 4, so it goes in the middle, and hydrogen and nitrogen go on the outside, because the rule is hydrogen can only form a single bond, so that goes on the outside. Carbon forms 4, so that goes on the inside, so that leaves nitrogen on the right side. Now, the nitrogen would never be to the left of the hydrogen because hydrogen can only form a single bond. So, nitrogen gets 3 bonds to carbon. Hydrogen gets 1 bond to carbon. That makes nitrogen happy because nitrogen gets 3 bonds. It's a group 5. Hydrogen gets 1 bond. That's a group 1. Carbon gets 4 bonds. Well, guess what? If I put my 3 there and my 1 there, I now have my 4 bonding electron pairs for carbon. Carbon and hydrogen are stable because hydrogen wants a single bond, carbon wants 4 bonds, no pairs, but nitrogen gets 3 bonds and 1 non-bonding pair. So the 3 bonds is 6, plus the non-bonding pair makes 8. Carbon, 4 bonds, 4 times 2 is 8. Hydrogen, 1 bond, 1 times 2 is 2. Hydrogen is the only one that wants 2, not 8. So now we're going to get a little bit more complex. C2H4. The carbons must go in the center because hydrogen has to be on the outside since they only ever form a bond. So when I draw this, this is what's going to happen. To make them symmetric, I'm going to put the C's in the middle, but my carbons are kind of go up and down off the edges because I know what it looks like. So I'm kind of cheating here and showing you that this is what it would look like properly. Now, each hydrogen bonds once to the closest carbon, and the 2 carbons have to double bond to complete the 4 bonds for carbon. So this is what I do. I draw my bond for each H to the C, and then 2 more in the middle. That gives hydrogen their single bonds. That gives carbon with 2 singles and a double makes 4 bonds. So that is all that's needed. Because remember, carbon never has non-bonding pairs. Hydrogen never has non-bonding pairs. Because group 4s and group 1s cannot. Get a little bit more complex. CH2F2. The carbon must go in the center because hydrogen's a group 1, fluorine's a group 7. They have to be on the outside because they only form a single bond. So when I draw this, I'm going to draw it like such. Carbon in the middle, hydrogen's on the outside, fluorine's on the outside. Now, I drew the hydrogens opposite each other, the fluorines opposite each other. It doesn't really matter because we're not going 3 dimensions right here. We're really only doing 2. So the F's could be 2 on the right and the H's 2 on the left, as long as they're not inside the center. So each hydrogen and fluorine is going to bond once because they're group 1 and group 7. And carbon is going to bond 4 times. So I get my 4 bonds on carbon, my 1 bond to each F and each H, and the 2 fluorines need 3 non-bonding pairs because they're group 7. So what I do is I put 3 pairs on each. 1 on the left, 1 on the right, 1 on the top, 1 on the bottom, and that gives me my 8 because a single bond is 2 plus the 3 pairs makes 6, which makes 8. Now we're going to do a more complex one. This is ethanol. And to do ethanol, I'm going to show you the skeleton. When we do them on tests and quizzes, I will give you the skeleton. You just need to finish it. Now, when I look at this, I have Carbons, they all get 4 bonds, so I need 4 lines for them. Hydrogens get 1. Oxygen gets 2 because it's group 6. So I'm going to start by doing that. But then the only one that needs dots is oxygen, because oxygen's a group 6, which gets 2 bonds and 2 non-bonding pairs. So the carbons always have 4 bonds, the hydrogens always have 1, and oxygen has 2 bonds and 2 non-bonding pairs because it's a group 6. Now, the king of all that we're going to do in complexity is NH2,2CO, also known as urea. Now, I'm giving you the structure. I'm giving you the whole skeleton. All you need to do is finish. So I look at oxygen. It's group 6, gets 2 bonds, 2 pairs. I look at carbon, always gets 4 bonds. But if I put a double bond between carbon and oxygen, that leaves 2 left. So then that 1 goes between the carbon and the nitrogen. Hydrogen, we know, can only form 1. So that means there's going to be a single between the N and the H on all of those. And then we just need to finish up with our dots. So when we finish up with our dots, this is what we do. Nitrogen has 3 bonds, so I need a non-bonding pair. Oxygen has 2 bonds, so I need 2 non-bonding pairs. All the others are done. Carbon with 4 bonds, 4 times 2 is 8. Oxygen with 2 bonds and 2 pairs, 4 plus 2 is 8. Nitrogen with 3 singles and a pair makes 2, 4, 6, 8.